Ladies and gentlemen, welcome to the first talk of this session. The speaker is Professor Paul Gorman. He's from Massachusetts Institute of Technology, and today he's going to give a talk on combining physics with machine learning to improve climate modeling. So please join me in welcome Professor Paul Gorman.
Okay, yeah, thanks very much. Can you hear me okay? Yeah, okay, great. Yes, I'm delighted to be here. I arrived on Thursday and having a really good time exploring Beijing. Yeah, I'm going to talk about climate modeling and how we can use machine learning in new ways and combine with physics to try and improve our predictions using climate models. So this is work with a large number of people, but I highlighted John Dwyer because he was my co-author on the paper that won the Frontiers of Science Prize. So I just wanted to give a shout out to John for this. And please, if you have any questions or anything's not clear, feel free to interrupt me as we go. So the motivation for this is that we know the climate is changing, and one of the things that's changing a lot is the hydrological cycle, so precipitation from storms. And this is having major impacts. So for the US, this is really highlighted just this past July 4th and 5th when there was a really big flooding event in Texas. This is a picture of it, which caught a lot of people off guard. It was a flash flood due to a stationary convective system happening in July. And I just highlight July because this will come up a bit later. And so these are kind of storms, if you read the New York Times, it said, okay, these storms are getting stronger in terms of the rainfall. And I could point to similar events in China, for example. And so a natural question we have is, we want to project at a local scale, not just globally, as I'll show you in a second, how these kind of storms are changing. Because they have major impacts on people. They also, thinking more broadly, affect the landscape, and they also affect ecosystems. So ecosystems are sensitive to rainfall and precipitation more generally. Not only the mean rainfall in a year, but how it's distributed, what kind of intensity the events happen at. So to come to the question, what is climate change doing to that type of event? So this is a very high-level graph showing an effort I made using rain gauges over the past 100 years to say, well, how is extreme rainfall changing? So this is what's called OREX one day. It's the heaviest day of rain in the year. So it's a 1 in 365 event. And precipitation here, including rain and snow. And then this graph is showing how that has changed per Kelvin warming over that 100 years, roughly. And it's done in latitude bands and aggregating over all the rain gauges in a latitude band because that's a good way to get the signal out of the noise. There's a lot of unforced variability in this statistic. And what you can see is that the graph is above zero, but it has very big error bars, particularly in the tropics, right? These are the error bars. So they're basically huge. In the northern hemisphere, where we have more rain gauges and better records, you can see there's a fairly clear signal, but say in the tropics, it's pretty unclear. And it's not giving us information at the scale of what's happening in Texas or China, for example. But it is increasing. Now, if we look in climate models, which are physics-based models currently, physics and chemistry, run forward as a system of equations, run forward in time, we can see, well, how would extreme rainfall events, for example, change? And so this is the same statistic I was showing from observations. It's the annual maximum daily precipitation, so the heaviest day of rain in the year, how it changes per Kelvin warming over the period 1950, but now going into the future 2100, assuming we emit at a fairly aggressive rate CO2 and other greenhouse gases. And what you see is there's blue at a rate of about 6 to 9% per Kelvin over a lot of the map. But there are actually red regions. That means there's a decrease in the intensity of extreme rainfall. So if your model in your head was, well, there's more water vapor in the air with warming, heavier rainfall. That doesn't always work out, right? There's places where it actually decreases, although that is a factor of the greater water vapor. And then the other thing to note is there's differences. Like, for example, here over India, there's a much larger rate of increase. So this is the kind of information we would like to know. If you look seasonally, so remember that Texas flood was in summer, just a week ago, basically. If we look in northern summer, now this is the heaviest day of rainfall in northern summer, so June, July, August. Now you see a very heterogeneous map. There's actually places now here in Texas where these models would project almost no change with global warming, right? So that's kind of surprising, right? There's more water vapor in the air, but the rainfall extremes are not increasing according to these global models. And then there's widespread regions like Mediterranean, which decreases. So what's happening is the circulation is changing. There's changes in how much rain that forms reaches the surface. Things like this are making this map. The problem with this is if we look, this was made with many climate models averaged together, but if we look at the different climate models from across the world, which would include models from the US, Europe, China, etc., we can get a very basic sense of uncertainty. If they all agree, okay, maybe they're still wrong, but at least they all agree. If they all disagree, then we have very little confidence in them. So let's look at that. This is the standard deviation across the models that made that projection. And what you can see, the numbers are very large. So basically in the tropics, there's really wide disagreement. And so we don't have much confidence in these projections. So the question is why is that and what can we do about it? So one of the big problems is that the storms that are forming the rainfall, like this storm here over West Africa, a convective storm, are quite small scale compared to the grid spacing of the model. So the model could be 100 kilometer squared grid spacing for a global model. And we have to represent somehow these small scale features that we really care about for precipitation, for example. And so the traditional way to deal with that is to make a subgrid model. So this is meant to represent everything that's happening at scale smaller than the grid spacing. And that's called a parametrization in climate and atmospheric science. So I'm going to call it parametrization, but you can think of it as a subgrid model. And in this case, it's based on a set of plumes. So you're basically modeling this cloud here with these plumes. However, it's a really complicated problem. I was just talking about this at lunch. There is ice in the, above, say, 5 kilometers, the clouds are ice. You have transitions from ice to liquid. You have downdrafts. You've got interactions with radiation. The clouds are interacting with sunlight and long-wave radiation. So it's a really complicated fluid dynamics physics problem. And so doing this, there's been a lot of progress on doing it over the last 40 to 50 years, but it's just really hard. So can we do something better? So if you were at the last talk by Stephen Chu, he was saying it's a good idea to pick a new tool, because then you don't have to be as smart, right? You can just take advantage of the new tool. So that's what we're going to try and do here. Instead of trying to improve these models, which people like Arakawa and Schubert, who are extremely smart people, came up with, we're going to try and just use the new tool of machine learning or modern machine learning to try and do better. Just to convince you that it really is this parameterization, here's an example of a PDF or a frequency distribution of rain rates. So this is how often the rain rates occur for different rain rates, and it's on a log scale. Here is observations, and then this is the same atmospheric model, but with just 2 different ways of representing that subgrid convection. And you can see neither of them are doing well, and they disagree with each other greatly as well. So that's just one sign that if we can do something good with this convection, subgrid convection, we can make a big improvement. So we can see these big differences, oops. Okay. It's back, okay. We can see we can make differences not only for light rain, but also very heavy rain, which I've been talking about so far. Okay, so we want to use, yeah, go ahead. Yeah. Good question. Yeah. So for rainfall, the measurements are very tricky. If you think of a rain gauge, it could be just this size, right? So that's a very high resolution measurement, but it's basically a point measurement. Then you can also try and infer rainfall from satellite radiances, and that would be on more of a scale comparable to the model. So if you can think of the model maybe as 50 kilometers, 100 kilometers grid cells, and then what you want to do is take the observations for precipitation and average them up to that grid cell, because precipitation is a flux, so that's the sensible way to deal with it. But this is, yeah. Really, the rainfall rate is actually fractal, a multifractal field, and so any kind of averaging does some damage to it, I guess, yeah. So that's a very good question. Okay, so we want to do something with machine learning. We need something to train on, and what we're going to train, and we can't just train on observations, at least we could, but if we want to go to a different climate, that's going to be very limiting. So what we're going to do is train on this new class of models, global high-resolution simulations, something like 4-kilometer grid spacing. So on the left is observations of a cloud field, and then this is a particular model we use, SAM, called SAM. It was initialized about a few days earlier, so it's still got, or maybe shorter even, same kind of cloud field. And you can tell differences, but they're pretty good. And in general, this class of model does not need a deep convection scheme to represent those really deep clouds I was showing you. A funny story about this graph is for a while I was giving this talk, and I would by accident I had the same left and right panel, and I would ask people, can you tell which is different? And everyone was always very puzzled. But anyway, these are now genuinely different. It was somebody at Princeton who pointed out actually the same Paul, yeah. Okay, sorry. Okay, so this is the kind of model, doesn't need because its resolution is much higher, 4 kilometers versus say 50 or 100 kilometers, we can train on it. Now, we can't use it for climate directly because we can only run it for a couple of years. It's an extremely expensive model. We need longer runs. So to illustrate this, again, this came up in the previous keynote talk. How long does it take for the temperature of the Earth to adjust to a change in CO2? So if you just double or half CO2, here's a graph of the fraction of the total response in surface temperature that you see. And I think actually Steve gave a figure of 50 or 100 years. I think that was very low. I didn't say anything, but I think that's extremely low, because you can see here in the northern hemisphere, in response to a doubling of CO2, this is just suddenly increased CO2 in a model and see how long it takes to equilibrate. You see it takes about 1,000 years. And in the southern hemisphere, where we have upwelling waters, it takes even longer. So there's a really long time scale. So if you want to do climate modeling seriously, you need to run for very long times, and we can't use the really high resolution model. So here's the situation we have currently in practice in what people do for global climate modeling. They have a climate model, it's on some kind of grid, they have the laws of physics for the resolved motions, and then they have something inspired by physics for the subgrid processes, and they combine them together. And the idea that my group and other groups have been pursuing in recent years is, let's keep the laws of physics for this part, right? Because we know what it is. This is the part we can rely on. And let's replace the part that was very uncertain with a high resolution model which we trust better, and then use machine learning to learn a mapping from this guy to give us what we need, the effect of the small scales on the large scales. Okay. So what are the opportunities that come from doing this? Well, one thing is it can improve accuracy. I'll show that shortly. The other thing is it can be much more flexible. So traditionally, this parameterization problem was done in a kind of a column mode. So you have one column of the atmosphere providing inputs, and the same column give you the outputs. But now we could try something different. We don't have to stick to that. And then the last thing I think that's exciting about this is maybe we'll learn something new about the physics in doing this, right? So traditionally, learning about these subgrid processes has been a great way for scientists to learn about the atmosphere and ocean. And so maybe something similar will happen here. Can we get some insights? What are the challenges that everyone is facing? Well, one thing is when you couple, say, a neural net to a physics model, sometimes it behaves well, and sometimes it doesn't, and it goes unstable. And I would say, I think there's been a lot of papers on this, but it's fair to say we don't really understand when it's going to be stable and well behaved. If you just stick to numerical modeling of partial differential equations, we have historical results that are fantastic, telling us when we're going to get the right solution based on stability, convergence, etc. But when you're coupling a neural net, we don't have those theorems available. The second problem is probably obvious. If we train just on the current climate, say from observations, to go to a warmer climate, we're going to have to extrapolate, and that's a no-no for machine learning. You never want to extrapolate. What happens is, let's say you train on a sine wave, and then you try to extrapolate with a neural net. You train on this region, so this is y and x. You train here, and then you want to say, okay, here's my test data out here. Kind of do good for the sine wave. Well, if one random, and you train it with a random initial weights, one of them might look like this, and you publish your paper. But if you retrain your neural net with some other random weights, interestingly, under fairly general conditions, you get just these kind of linear slopes with random slopes. So this would be like going to a warmer climate, right? This could be very bad. Okay. Oops, sorry. And then the last thing I think is a problem we can solve is that when we do a physics model, we know to conserve things like energy, momentum, and so forth. But a machine learning parameterization may not do that if you just do it in the most straightforward way. So as you might guess, that third one is something we can fix, but the other two are somewhat difficult. Okay, so what I'm going to do in the rest of this talk is demonstrate an approach that works, at least in idealized settings. It leads to stable and accurate simulations. Then I'll talk a little bit about how we can kind of go beyond conventional paradigm, and really change things up. And then I'll just say where we're at in terms of this field, like what are we doing currently, and what do I think are the kind of big questions we need to address. Okay. So we'll start with just kind of a demonstration that this can work. So we're going to learn in this work from an idealized setting, but a real atmosphere model. So we're looking at the outgoing radiation coming up from the Earth at the top of the atmosphere. And we're not doing the whole globe, we're just doing this strip, but this is the tropics here. We've got 2 rain bands, various storms, and then this is the mid-latitudes, and you see we get extratropical cyclones and anticyclones. So this has kind of got all the ingredients of weather in the atmosphere that we care about. So this is a particular model. I won't go into the details, but we do some tricks to make it less costly, and we prescribe the ocean temperature. So we're not dealing with the ocean here, although we could in principle. So we're going to try and learn from this. I wanted to show you that this is a reasonable thing to do. Here's the rainfall distribution as a function of intensity from observations and then from our simulation. And this is the same kind of thing I was showing you earlier with the 2 kind of funny lines. So this does very well. This would be an excellent simulation. And then if you took a typical climate model, like one I used called CESM, you see it has a problem that it's too often raining at the low end and too weakly raining at the high end. So this is called the drizzle problem, and this is a problem of poor extreme rainfall. Okay, so let's say we take that model. Here's the mean precipitation, which is mostly rainfall in this model, versus latitude in the millimeters of liquid water a day. The blue line is this high-resolution simulation. So it has 2 tropical rain bands. Those are called ITCZ, intertropical convergence zones. That just happens to be in this setting, you get 2 rain bands. But if we go to coarse resolution and don't do anything, so we're going to go to coarser by a factor of 12, so kind of a 100-kilometer grid spacing, now you get a single rain band right at the equator, and it's extremely strong. And then similarly, if you look at the high percentile of 3-hourly precipitation, you see similar thing. You get this really strong values right at the equator. So can we do better by adding a neural net? So what we do is we take our fields from the model. Here's a little blow up of a little area here in the tropics, and we just coarse grain it by a factor of 12. So that's what this is. And we coarse grain the equations of the model also, and work out what is the subgrid term. What is the effect of the small scales on the large scales using this coarse graining procedure. And what are the kind of processes we deal with? We do vertical advection. That's the vertical wind bringing things up and down. We have turbulence near the surface called boundary layer turbulence. Radiation is included in this. And then microphysics means cloud processes. So raindrops converting into rain, ice formation, things like that. So everything happening in the cloud is called microphysics because it happens at such a small scale. Okay, so here's the structure of our model, and I don't expect you to get all the details, but just to give you a sense of what it looks like, the neural net. So it has some inputs, temperature and moisture, location, and then it has 5 layers and then an output. And then it calculates things like radiation, vertical advection of water and energy, things like that. And we also do something for a separate neural net for the surface fluxes. So the basic approach, these are the details, but the basic approach is we want to be very accurate, so we calculate the subgrid terms as accurately as possible. This is very painstaking work, but we do it using the equations. And then we want to ensure conservation of water and energy. And so the way we do that is actually pretty simple. Instead of predicting how the subgrid process would change, say, the temperature at a given point, we actually instead calculate the vertical energy flux. That's the thing the neural net is predicting, or the vertical water flux. And if you do it that way, then you're guaranteeing conservation. So it's all built in. So an example here, in terms of equations, here's the rate of change with respect to time of the energy, which is h. And then it's a vertical derivative of this flux due to vertical advection. And so we just need to predict this flux, but because we only want the subgrid term, this overbar denotes coarse graining. So we take the overbar of this is the total flux, and we subtract the part that's resolved. So if you're not familiar with this kind of notation, don't worry about this, but basically this is a kind of very simple version of what we have to do. Okay, so does it work? So here's the high resolution simulation, one snapshot. We're looking at the amount of water integrated in the vertical. And so that's high where there's these rain bands. Here's the coarse simulation. And then here's the coarse simulation with the neural net parameterization. But we're just starting it with the same state of the model as we had, from one of the coarse runs. And so I'm going to step forward and just show you how this evolves over time when you add in the neural net. So you can kind of see the single rain band is now splitting apart very nicely. So it takes a while for it to happen. There's some heat capacity in the system. And so eventually you end up with something that's much more like this guy over here. And you'll also notice these kind of, noise or very intense spotty stuff. I don't know what to call it, rough field. This is much smoother again. Yeah. So this is showing by adding in the neural net that we can run at much coarser resolution. So factor of 12 coarser. That's factor of 12 in 2 directions. And then you also have to, increase your time step can be much larger when you have a coarser model due to the CFL condition. And so overall, this is a huge saving in terms of computational cost. Okay. Let's see. And then the other problem I mentioned was stability. I will be honest, we're trying to be very careful here. We get a very stable result. It never blows up. I won't say we know exactly why that is, but that is true. We can just run this as long as we want. Nothing bad happens to it. And here we collect this mean precipitation. So the green was the coarse resolution without any neural net. We add in the neural net, we get this red line, and it agrees much better with the high resolution target. So that's good news. And similarly, if we look at extremes of rainfall, kind of thinking back to that Texas flooding, that kind of thing. So this is a 1 in 1,000 event of 3-hourly precipitation. Just running at a coarse resolution without doing anything is very bad, but if we add in the neural net, or actually this was a random forest in an earlier version, it does really well. Yeah. So this is very promising. It's a kind of an idealized setup, but it's looking really, really good in this case. Okay, so that was demonstrating how this could work. I want to just talk about how you can kind of go beyond conventional paradigm, because we're still kind of working in the same paradigm as before, just using machine learning. So one problem is that current parameterizations based on physics, they have what's called a gray zone problem. So they work okay at, say, 100 kilometers, but now we've got increasing computational resources and we want to run at, say, 20 kilometers, and the convection's happening at, say, 1 kilometer. That means you're getting close to the scale of the thing you're trying to represent, and you're in this gray zone, and the current schemes don't tend to work very well in that limit. They're often based on an idea of averaging, say, over many plumes, some kind of statistical equilibrium. And so you can see this, actually, this is running without a convection scheme. This is R squared, a measure of skill, versus resolution in degrees. So high resolution's over here. And basically adding in the deep convection scheme for this whole range here is doing very bad. It's actually decreasing the skill a lot. And it's only when you get almost basically off this graph that it starts to help out. So that's current parameterizations, and you can try and improve them, make them scale aware, but that is challenging. So what can we do with machine learning? Well, again, you know, I'm loving that this previous talk by Steve too was really illustrating this idea. You know, we've got a new tool. We can just do, we don't have to be too smart about it. What we can do is just train on the data, coarse grain by a factor of 4, by a factor of 8, by a factor of 16, by a factor of 32, throw it all together, make one of the inputs be the coarse graining factor, and then train our neural net. Basically, that's a really simple and easy way to deal with this. And when you do that, if you plot the skill of when you run a simulation versus the coarse graining factor, the skill actually goes up as you get to smaller coarse graining factors. So as you get into this gray zone, the gray zone would be here. And that actually makes sense if you think about it, because there's less to parameterize, right? You're pretty close to the right resolution to resolve the thing you're interested in. So it should be an easier problem, and with machine learning, it is an easier problem. Here's an example with just coarse graining factor of 4. It works okay. So we don't seem to have a gray zone. We just have to train on many different resolutions. The other problem I want to highlight, so far I've been talking about moisture and energy, fluxes of moisture and energy in the atmosphere, but convection thunderstorms, for example, also transport momentum. Here is an example of this. This is an estimate of how much momentum tendency, the time derivative of momentum, is due to, well, just everything that's subgrid. Here, the solid lines means it's going eastward, I guess. I'll have to think about that. Yeah, it depends on which sign. So here's easterlies, yeah. And then what's happening is, here's a cloud. You have these updrafts where air is rising in the cloud, but the cloud is tilted. So that means because of this tilt, it means you're actually transporting momentum upwards. Horizontal momentum is being transported upwards. And depending, if you flip the tilt, if the tilt went the other way, you would transport momentum, horizontal momentum in the other direction. The sign would change. So you have to know the tilt of the cloud. And it turns out there's not an easy way to estimate which way the cloud is going to tilt. Current convection schemes assume they'll tilt based on the shear, meaning how the wind changes in the vertical, but actually that doesn't really predict it very well. So basically that's all to say that predicting momentum transports is actually quite difficult. So I can do this with the neural net. We're now going to try and predict the flux of momentum. So it's basically the vertical velocity times the horizontal velocity times the density. Here is the true subgrid flux of momentum versus pressure. So this is like height in the atmosphere. Here's the surface, and this is latitude. And so it has this particular pattern. Here's what the neural net predicts. And here's what a conventional physics-based scheme does. So it has some of the same properties, but it's just not quite right. So that's for the time mean. And then if you look over time now, instantaneously. So now time is going from the left to the right in hours, and here pressure is the vertical coordinate, so here's the surface, here's the top of the atmosphere. And here's the momentum flux. So you can see it's pretty noisy, and it changes sign a lot. Whereas the energy flux, it's always the same sign, and you just see when it's convex, you get this simple blue structure. So this is much easier for a neural net to predict. This is much harder. There's also things called gravity waves, and you can see they show up for momentum, but not for energy. So this is a really challenging problem. If you try to predict this on the instantaneous time scale with the neural net, you see it actually does have some of the right features, right? It's kind of filtering out all the noise. And that is, you know, the actual R squared is about 0.3, so 30% of the variance, roughly speaking. And the conventional parameterization based on physics and heuristics is actually negative R squared, basically it has no skill whatsoever. So again, this is good, but it's not as good as when we were doing energy and moisture. So that brings up the question, well, we've been sticking now to the column-based approach. So all the inputs are in a column and all the outputs are in the column. So we could easily vary that. So here's the traditional approach. You have one column of the atmosphere. Here are the inputs, temperature and moisture, and you predict the fluxes in the same column. Here's the simplest thing you can do. You add the neighboring columns as inputs. So if you're a machine learning person, you would immediately say, why don't you do a convolutional neural net, et cetera? We tried all that. It turns out that like all the information is useful information happens to be just in the neighboring cells. So this is kind of the easiest way to do it. And so when does that help? When does it help to use the neighbors as input? Well, at the top, I'm showing you cloud scenes looking down from above. Here's the coarse grid boxes in kind of magenta, and then the actual high resolution data. And you see the ones that are improved, you can see there's these kind of linear features. So maybe there are fronts in the atmosphere or squall lines. And these guys, the more diffuse cases, are not improved. So it seems when the convection is organized in a certain way, it's helpful to use these neighboring inputs. And then here's which variables improve. So I won't expect you to see all these variables, but basically this plotting R squared, blue is just the 1D column approach, and red is using the neighboring grid cells as inputs. It generally helps, but it really helps for momentum. So momentum was the one I was saying, okay, this is really difficult. It was very noisy, skill was low, but you can really get a big improvement, and actually we've got even bigger improvements more recently in the case of momentum. So again, just going beyond kind of traditional paradigm is easy with machine learning. Okay, so lastly, I want to talk about, going well in time, our ongoing work and kind of an outlook of where this could go in the future. Okay, so one problem I mentioned earlier was how do you go to a warmer climate, right? Let's say if you just train on the current climate, we have the graph over there, we don't want to do this, right, when we go to the warmer climate. We didn't have that problem with physics because we were guided by physical principles. That's an advantage of physics for sure. So this is showing you in some simulations we did, the change in precipitation in percent per Kelvin warming versus latitude. And this is in an aquaplanet, so kind of a simplified setup with just ocean. And the black line is kind of what our target was doing. And then this was an earlier paper with a random forest parameterization, which I won't get into, but has some advantages and disadvantages. You see it's doing well. And what we're doing here is we're training it on both the control climate and the warmer climate. So we're assuming we have a high resolution simulation, say in the control climate and a warmer climate, and we can do that. We train one parameterization, it's able to do climate change. Here's what happens if we don't train on the warmer climate, just train on the control climate. You see it really does badly, right? We know what the truth is, that's the black line, and it's kind of a disaster. Right? Why is it doing badly in the tropics, do you think? So this is 0 degrees latitude here. It's doing okay in the colder regions. So we're just training on the control climate and going to a warmer climate. thoughts? I see some people discussing it, but yeah. So basically, it's actually a really simple reason. The reason is the direction we're going into a warmer climate. So the kind of equivalent of what I drew over here is happening in the tropics, right? So we're seeing temperatures we've never seen before. So it's because we're going in the warming direction, extrapolation errors are happening in the tropics. If we were doing a cooling, you would have had the errors in the colder regions. Yeah. And so that implies that what's happening here is that, you know, it is getting warmer here, but the machine learning can learn from other latitudes, right? It can learn from one latitude and apply it at a different latitude. So you can kind of learn climate change based on different regions of the Earth. So that's actually a cool result. But we still have this problem in the tropics where you see unseen temperatures seen before. Okay, and another result from Raspa et al. In a really nice paper, they showed if you train on the current climate and a much warmer climate, say 4 degrees warmer, you can then do intermediate climates, like 2 degrees warmer, right? So you can interpolate between the two climate states. So that's very helpful. You don't have to train on every possible climate. You can do current state and some end member, and then you do well in between. But what could we do better? Is there any way to do better than this? Because if we were training on the warmer climates, we're training on these models which we've kind of tuned for the current climate, pushed into this other state, right? So it's not very satisfactory. It's okay, like I think it's a feasible path forward, but you'd like to do a bit better. So the problem is if we look at the frequency distribution of temperature, sorry, the axis got cut off here, but this is a frequency distribution of temperature in Kelvin. It has this is globally, so it has this kind of weird shape because we're combining many different regions. But what happens if you go from minus 4K climate to a controlled climate to a plus 4K climate? The temperature distribution just shifts to the right. And we're having distribution shift. We're going out of regime. That's a problem from machine learning. And again, this is the skill versus latitude and pressure. And you see you have no skill in the warmer climate in the tropics, just like in that earlier paper I showed you. This is now doing deep learning. Doesn't matter. You get the same problem. So what you can do is feature engineering. You can say, okay, if I can pick some inputs that are climate invariant, meaning they don't change very much between climates, then I don't have this problem of going out of distribution. So instead of temperature, I'll use something called buoyancy, which just measures how, say, less dense air is than its surroundings, for example. And that, it does change a little bit, but here's its distribution. It's much more invariant. And when you do that and use relative humidity instead of specific humidity, so how close you are to saturation, then you're now not doing too badly. So this is exciting. So this is called climate invariant machine learning. And this is from a paper led by Tom Buchler. However, it doesn't fix all the problems. I don't have a graph to show that. So we've been working, ongoing work, trying to push this forward. There's kind of two problems. One is it's not skillful enough. It looks pretty good here, but it's not. If I showed you the precipitation, it wouldn't be good enough. And secondly, it took years to work out what were the right inputs. So basically, there was like 10 people on the paper, and they were all worked on it for, I think, like 3 years, and came up with the right inputs to make it work. So it was kind of painstaking, need a lot of physics insight. What if you go to another problem where you don't have as much understanding that buoyancy is the right variable? So what a postdoc working we call Shuchang Liu is working on now, and is about to submit a paper on, is can you, of course, the answer in machine learning if you have a problem is more machine learning. So she's worked out a way to learn what are climate invariant inputs from data, which is exciting. So that'll be probably submitted in the next month. So this, I think, is an exciting way. And here we're testing it on, you know, warming by 4 Kelvin, but I think the way you would use it is you train on, say, observations, and then use it for a very modest warming, maybe a 1 Kelvin warming or a half Kelvin warming, which would bring us into the next few decades. So that would be, I think, very useful. Going to plus 4 Kelvin is maybe a stretch, but this is just a good test. Okay, so the next thing, I showed you results from just training in these kind of idealized domain. Remember this kind of very oblong domain. didn't have any land. So an obvious question is, can we do this while including land and topography and everything else? So this is work with Griffin Moores and Yanni Val and Murat Krudinov. And what we've done is we've taken this simulation you see on the right, which has land and everything. It was part of a project called the Diamond Project. And this was run with grid spacings ranging from about 4 kilometers in the tropics to 2 kilometers in mid-latitude. So this is a really good training data set. It was only run for 40 days, so it's very short. But actually, we were worried about that. Would it be enough data to train? But because you're training over the globe with this, it's a huge amount of data, terabytes of data, we found actually we only needed about 10 days of data was enough. So you really don't need very long if you've got the right data. And we're doing the same kind of thing as before, but now on this better data set, we do have to deal with topography, which is a problem because the column of the atmosphere is kind of squished and moved up, right? So you have to deal with that. So there are extra problems. But basically, we've got it running. So this is an example. So here's the high-resolution simulation. See some nice storms forming. And here's our simulation run at much coarser resolution with the neural net, and it's running stably. It's looking really good over ocean. We still have some problems over land, so probably more work is needed there. But I think this is exciting. The other thing we're trying to do is to put this kind of approach into what's called an Earth system model. So this particular one is called CESM, for Community Earth System Model. So what's in an Earth system model? Well, you have the atmosphere. I've been talking about the atmosphere the whole time. It's coupled together with the ocean, with biogeochemistry in the ocean, for example, the carbon cycle, land ice perhaps, sea ice for sure, land processes, river runoff, surface waves. So basically you're just throwing the kitchen sink and trying to model everything. And this is really important because let's say I want to know how carbon dioxide is going to evolve into the future, how much carbon is the land going to take up? This is the kind of model you need to know. How will the land, how much of the CO2 will go into the ocean? How much will go into the land, etc. So this is really the kind of model we need. And so what we're doing is we're only replacing one part, which is deep convection, not all the things I mentioned, boundary layer turbulence and so forth. And the idea is just to target the really most uncertain part of the model and kind of maximize flexibility. And just kind of give you an example of the kind of differences, this model has a time step of 30 minutes, whereas the kind of models I've been showing you previously had time steps of 10 seconds, roughly, right? So this is a completely different type of model. And so we have this running. This is work led by Xavier Levine. Here's an example of the intensity distribution of rainfall. The red, sorry, I can't see. The blue is observations. The green is the neural net version of this. And the red is the original version. So you can see it's doing some improvements. Maybe not quite as good as earlier, but pretty good. So this is exciting. I think this is the kind of thing you really want if you're going to do climate modeling. Okay, so I will conclude. So we're trying to improve climate modeling using machine learning. And the main reason is the climate models are enough to tell us the climate is warming and kind of broad scale features like rainfall intensification, but it's not giving us these detailed things we need like precipitation extremes. So by including machine learning and physics, we're getting parameterizations that are stable and outperform conventional approaches. They don't have some of the problems that we have before, like the gray zone where things don't work too well, ironically, if you go to higher resolution. And they have this more flexible structure, like we can try out different things. I want to highlight kind of two questions to think about. So the first one relates to weather forecasting. So there's going to be at least one and maybe two talks later in this Congress about weather forecasting. And basically machine learning is now outperforming conventional numerical weather prediction. Right? So the best, in some sense, by some measures, the best weather forecast you can get on, say, a 7-day timescale come from a machine learning model. And this has just happened. So this is brand new. And this is a very different problem to climate because you can just train, you have validation data, test data, it's coming at you all the time, right? So you can just train on the current, actually we train on reanalysis, meaning it's, or we are using a physics model to obtain the training data. So it's not just machine learning, I should be clear about that. But you have a lot of training and test data, and yeah, what you do is you just do machine learning for the whole thing, or maybe a similar approach to what I just showed you. Google has a model called Neural GCM, which is actually very similar in a way to what we've been just talking about. So you keep the dynamics and then replace the column processes. So that's the same person, Yanni Yuval, who's involved in this work, is one of the people involved in that. So that's very exciting. But for climate, that's not so good, right? Because if we replace the whole atmosphere on the training data, how do we go to a warmer climate? It's just really hard, right? We just don't have the data. Now, what people have been doing is they train what they call an emulator. So take an existing climate model and try and just emulate that. And that works really well. It's not any more accurate, but it's 350 times faster. So here's an example called Camulator. So that works really well. So that makes things much faster, but it needs a lot of training data, like 30 to 100 years, and it can't generalize to warmer climates, so it's not more accurate. And then I've been talking about changing existing climate models, adding something to improve accuracy. So I guess the question, I was just at a Gordon conference on machine learning and climate, and I think basically the question that kept coming up is how do we combine this? Right? We've got all these kind of promising directions. What's the best way to combine these approaches, you know, to do climate? You know, weather is just working already. How do we do climate? And then the other question I would like to pose to you is how can we learn about the physics, right? So we'd like to understand convection in the atmosphere from a physics point of view. There's a lot of puzzling things that are not understood about it, and other aspects of climate and ocean circulation, etc. We've got machine learning, which can make really accurate predictions in some cases. How can we learn something, go back to the physics? So there are some cases, like this is looking down on that non-local neural net I showed earlier. So we're trying to predict the center column, and here are the inputs surrounding it. And this is what's called the relevance. So there's a method called layer-wise relevance propagation, very standard method, where you say, okay, what inputs mattered for this neural net prediction? And so here's temperature, mattered a little bit at the center. Moisture definitely mattered at the center. The horizontal wind mattered here to the west and the east, but not so much to the north and the south. The meridional wind, that's the northward wind, mattered a lot to the north and the south, a little bit in the middle. I'm looking at Chang, so he knows the answer. So this is actually the divergence of the wind. This is this machine learning is telling us this is du dx plus dv dy. And it's saying we should use that in our parameterizations. Nobody uses that in their parameterizations. Yeah. So this is a kind of a basic example, but could we do something more advanced to kind of tell us, unlock some of the mysteries of climate, atmospheric physics, et cetera? I think that's still, untouched. There's methods like equation discovery. They have been used a little bit in this field, but they're more often, if you look at papers on equation discovery, they're usually taking an equation you know already, a partial differential equation, add some noise, and then try to rediscover the equation you started with. But, can you actually learn something new, I think is a big question. So I'll leave it there. Thank you.
Okay, now we have time for a few questions. So any questions?
Yeah, so it's fantastic talk. Many promising research lines. So I guess your approach is use the kilometer scale global atmosphere model to provide the input in subgrid scale physics. So I guess for those kilometer scale atmosphere models, if you integrate modeling for like a few days, they develop
Right. Yeah.
If you integrate for a month, even multiple months, then again the ontology
Right.
of the model become really kind of very poor.
Yeah.
So there is there somewhat a contradiction, or there might be something important that
Yeah.
This machine learned quantization model the authors explained.
Yeah, that's a great question. So yeah, I mean, I guess maybe to go back to just to look at it. Yeah. So yeah, or actually even further back, the two graphs that I said were the same in my earlier. Yeah. Okay, I was too far to go back. Okay, no, I shouldn't have bothered. It was at the very beginning. You're right. Okay. So yeah, this is the kind of model. So yeah, this was called a Turing test for climate modeling. Could you look at these fields and tell they were the same? But this was initialized, and the problem that's been pointed out is that these models are not a panacea. They don't solve everything. And in particular, problems like the tropical rain bands, there tends to be 2 rain bands in regions where there should be 1. Things like that don't go away. And I think, yeah, I think that's true. So I think the things they can do better is, say, the distribution, intensity distribution of rainfall. So not having too much drizzle, having the right extremes. So I think that is the one thing they can, that's one thing I'm pretty sure they can do well on. Also, the daily cycle of precipitation convection over land, it's not completely fixed, but it is better. So rainfall over land peaks at about 3 p.m. In standard climate models, it peaks about 12 noon. They don't fix everything, but they go in the right direction. So I think there are things like that they fix, and then there are other things they don't fix. So, you know, I guess the alternatives are to use an even shorter simulation for training that is better again. It's kind of going down the rabbit hole, right? But if you went to 100 meters, it would be better. Or we also need to do something that is helping with these biases. And so that could be, that's kind of what I was trying to get at the end, some combination of using observations and this kind of approach all together. Yeah, but basically it's a good question.
Maybe, we know a lot of how to run 100 models.
Yes.
So then running skill.
Yeah.
I guess, in a sense, short scale processes used to
Exactly. So maybe we can get better.
Yeah.
I think the other big problem is when you run a kilometer scale, it's so expensive. It's incredibly expensive that you can only do a couple of runs and that's it. Like that's already a huge problem to do it. So you can't investigate more. Okay. Yeah. Yeah, sure. Go for it. Yeah, that's a great question. So I think the improvement they get over the models we had at global scale is, I can't remember the exact number, but it's kind of the equivalent of like a decade or two of, maybe a decade of further development of the models we're doing already. I might be wrong on the exact number, but something like that. So it's a paradigm change, but it's not like the accuracy hugely increased. But yeah, so that's one thing to say. The other thing to say is currently they have been at kind of a 25-kilometer scale, grid spacing. That means they can't do good tropical cyclones, for example. You just can't simulate a good tropical cyclone with a 25-kilometer model. It doesn't matter if it's machine learning or not. So they're an improvement. It is exciting, but it's not like they've totally changed everything. Now, if you want to do, things like flash floods for Texas and stuff, then I think you want to be combining those kind of models with something more regional that's focused on that. And then, yes, there are people doing a lot of work on that, kind of more locally, trying to, there's already in what's called nowcasting, so just forecasting for the next, say, 20 minutes or something. Machine learning is very good because that's kind of a vision problem. You've got like radar images and you're just predicting how they evolve. So some kind of combination of that kind of thing, plus the global models, I think could do well on it. But yeah, it won't be just the global models I was talking about on their own, just because they're still too coarse. It's very hard to, nobody seems to be going beyond something like 25 kilometers with those kind of models that I know of. Yeah, yeah. 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 Ah, okay, yeah. Yeah. Yeah, the reason I brought up the 1,000 years is not that you would necessarily want to run for 1,000 years into the future. It's just that when you're spinning up the model and getting it ready to go in the current climate, you end up running it for a long time scale. For example, to get the ocean at the right equilibrium and so forth. You wouldn't, people rarely do, those integrations I showed you, people would rarely do those. The one thing I will say though is, if you want to study extreme events, you may want to be able to generate, do effectively maybe not a very long 1,000-year run on its own, but you might want to do 10 100-year runs to access very long return periods. So that might be somewhere where this kind of model or a pure machine learning model could do well. So kind of to summarize, I was showing that more to say like there's long time scales in the system, and you need to run in developing the model and getting it into the initial state. You end up running the model very long, and that's why, you need to worry about it. The other thing to note is people are working on these parameterizations for the ocean also. So there's similar problems in the boundary layer of the ocean in what are called mesoscale eddies in the ocean. So yeah, that's kind of a whole other thing. And then I guess people do run for long times, like 1,000 years and longer, but it's mostly to investigate the past climate of the Earth. That's probably the most common reason to do it. Does that answer your question? Yeah. Okay, cool. Yeah.
But the original model maybe the observation of energy. So the result may be something that doesn't happen.
Yes, yeah, that's a good question. So basically, it's actually not obvious that what I showed you works. It's not obvious it should work because you lose a lot of information. The inputs are coarse. How can you get information on the small scales from just the coarse scales? So you do lose some information. The predictions are not perfect, but they're good enough to be useful. I guess that's the message from this work. But it's, yeah. No, the way I've been showing it, you just use, it's mostly based on high resolution simulations rather than observations. But yes, it's just the coarse ones as inputs. Yeah. Yeah, that's a good question
though. Any other questions? I think we may still have maybe 5 minutes for questions.
Yeah, I'm happy to talk to people after if they want.
Yeah. Actually, I have maybe one quick question. So
Sure.
for your, you mentioned two open questions
Yes.
in your last slide. I'm wondering, so can we use a technique called PIN, that is physics informed neural network?
Yeah.
That is for these two questions.
Yeah. So I guess it depends how you define it, but yeah. So in a way, this is kind of a physics-informed approach, but yeah, usually physics-informed neural net might involve you have some partial differential equations, say, and you want to use that as extra information. Yes, I think you could, but it's not totally obvious to me how to do it because we don't have a equation. We have the equation for the high resolution dynamics, but we don't have an equation for the coarse resolution dynamics. That's kind of what we're learning. So yeah, maybe there is a way to do it, but it's not obvious to me how to do it yet.
Yeah, okay. Okay, if there is no more questions now, so let's conclude this talk, and let's thank Professor Gorman again. Okay, thank you.